Good afternoon. Welcome all to the seventh IIsc EC webinar series. My name is Sandeep. I'm a faculty member at the Department of ECE IIsc. It is a great pleasure to have Professor Emil Björnson today with us. So he will be talking about a very hot and emerging topic in wireless communications, and is going to give us a signal processing perspective of reconfigurable intelligent surfaces, metasurfaces, metamaterials, large intelligent surfaces. Emil is going to talk much more about that. I'm sure many of you might already know Emil. He's a very active person, active on social media with all his YouTube videos and recent podcast series with Professor Eric Larson. Uh, uh, but anyway, it gives me a great pleasure to introduce him. Emil obtained his master's degree from Lund University. He's from Sweden, and he did his PhD from KTH, where he currently holds a visiting professor position at KTH Sweden, but also affiliated to Linköping University, Sweden. His areas of interest are wireless communications, signal processing for communications, and machine learning for communications nowadays. He has won several awards at top avenues, and some of the important ones are 2019 EUROSIP Early Career Award, IEEE Communication Society Frederick Elsick Prize, Marconi Prize for his paper. Again, best PhD thesis award from EUROSIP 2016, and Outstanding Young Researcher Award from IEEE Comstock. Many more to the list. He has also won several Best Paper Awards at top conferences like ICC, SAM, CAMSAP. So it's really a great pleasure to have you, Emil, with us. And thank you for accepting this invitation to give this talk on RIS. We are looking forward to your talk. Over to you, Emil.
Thank you very much. Yeah, unfortunately, the world is in the situation it is right now. But one of the positive part of that is that we have been starting to use the tele video tools so much now that it's possible to sit in your home and give an technical talk to people in other parts of the world. So it's a great pleasure to be with you today. And I will talk about these reconfigurable intelligent surfaces, what they are, and what is sort of the vision that people have in terms of using these ones in the future in wireless communications. And then there are many different aspects to this type of technology, and that is why I think it's an interesting thing to research on. It's sort of you can approach it from the electromagnetic side, and people have been doing that for a long time in terms of how to build something that resembles this vision. There are also people who have been working a lot on the communication parts in recent years about what kind of range can you achieve in terms of data speeds and things like that. And then I think what have been sort of forgotten a bit is the signal processing side of this as well. How you can view a communication system containing a reconfigurable intelligent surface using signal systems theory. So this is what I've been working on in the past year to try to enhance the signal systems perspective on this technology. So in this talk, I will first have an introduction to the general topic area, and then I will develop a system model. I will recap for you some signal system theory concepts of the basic kind, and then I will apply them to model an RS, and I will then use those model for optimization of the RS. And some of these things is things that you can find already in the early papers of this topic. But there are also some specific aspects to the optimization that you can only see properly if you have a systems and signals view on it from the beginning. Then towards the end, I will emphasize what I think are the good use cases of this technology. It's not a technology that's always the best one, but compared to alternative technologies, I will try to outline when I think this technology will be used. So starting with an introduction, I like to always start with this slide here talking about the physics of signal propagation, because we are sort of used often in communication research to normalize all numbers away so we can focus on how the equations look like and not exactly what numbers are there. But in this topic, it's very important to have the numbers right. So if you have a transmit antenna, and we assume this is an ideal isotropic antenna that transmits a signal with a certain power, then the signal is going to spread out as a sphere, and the energy will be located at the surface area of the sphere. And the more time moves on, the sphere becomes larger and the signals are sort of spreading out of the environment. And if we put a receive antenna at a distance d from the transmitter, and it has an area that is pointing towards the transmitter, which is A, then you can compute how much of the transmitted power that you receive using this freeze propagation formula. So you take the transmit power, you take the area of the receive antenna, then you divide with the area of the entire sphere's surface here. So 4 pi d is not the diameter, but the distance here. And so it's a radius, and it's d squared. This is the surface area. And then you get to receive power. So this is sort of basic math expressions. But if you put in some numbers in it, then it becomes interesting. So say that you have an antenna, which is like lambda, which is the wavelength. And maybe we have like a wavelength of 0.1 meter, or 10 decimeters, which is what you have at 3 gigahertz. This is sort of the main 5G frequency. Then if the element is lambda divided by 4 times lambda divided by 4, then you put this in here, you select the distance. Let's say that the distance is 1 meter. Then if you compute this term here, you will see that you will only receive 0.005% of the transmitted power, which is like minus 43 decibels. And if you increase d to 10 meters, then you will receive 0.00005%. which is minus 63 decibels, which is sort of means that if you take your transmitted power and you divide into 2 million small pieces, only one of them makes it to the receiver. And this is what we are used to in wireless, and this is how it works. You are losing immensely on the wave between the transmitter and the receiver. And this is only in the kind of line of sight scenarios. If you put it in other objects in the environment, you lose even more. And this is fine. Obviously, our wireless technology is working, and that is because it's not the transmit power that matters. There is the receive power and how strong it is as compared to the noise. And the noise is very, very weak. So that's why we are able to still operate our systems. But why am I saying this? Well, consider this scenario that I'm showing here. You have a base station on a building, and I'm standing here in the room with my iPad, which have a cellular chip, so it can connect to the base station. And if the signal should make it to this one, well, then you can sort of compute the distance. You can put it into the formula from the previous slide. But then since the signal is to make it through the wall, with concrete wall or something, you will lose maybe 20 decibels more. So it would be a very weak signal. Can we do something about this and to sort of increase the signal's strength? Well, usually you not only have a direct path, there could also be other paths. So for example, you have a window here, and the window might let the signal through much better than the wall. So the signal comes in here, it bounces on the wall, and then you have this classical type of electromagnetic phenomena like reflection, or if the surface is smooth, or scattering if it's a rough surface compared to the wavelength. And if you have a corner, you can also have other type of phenomena there. What probably is going to happen in this case here is that they're going to reach the signal, the wall here, it's going to be reflected towards the right corner of the room. So it won't help me very much. Maybe it will bounce off this wall, and eventually we'll have some diffuse scattering reaching my iPad here, but it will help very much in terms of the propagation. But what if we would put up a special surface on the wall here that we call a Reconfigurable Intelligent Surface, or RIS, and we could somehow configure how it is taking the signal energy that reach it and instead of reflecting it according to Snell's law towards the right part of the room here, it sort of forms a beam towards me as a user. If that would be possible to do, we could take most of the energy that reaches this point here and focus it here and give me a much better signal strength. And this is what we call a reconfigurable intelligent surface. Reconfigurable because we can sort of put the surface here and we can reconfigure its properties over time. Intelligent because it's sort of real-time programmable what it does. And it's a surface because it's a two-dimensional thin thing. It might have sub-wavelength depth, but it's large in the height and width. How would something like this work? So you have a transmitter. The signal is reaching the surface, and then you have a large array here of small elements, and you can reconfigure them back and forth over time so that you can let the signal that reaches the surface be reflected towards user 1 here or the user 2 here. And you sort of have some kind of programmable controller that is doing that. And if you zoom in at it, it contains these small squares that I have illustrated here. What is this square? Well, this is a small patch. Like you can think of it as an antenna, but it's not connected to a radio. It's just a passive patch that can get a radio signal reaching it, and then it is connected to a switch or diode so that you can change some of its properties. And these properties will sort of decide on how much time it takes before the signal is reflected back or scattered. And it also selects things like how much is absorbed and things like that. And these colors here are indicating that the different elements have different properties. So just as when you're transmitting from a array of multiple antennas, if you like the signal to go in one direction, to create some kind of constructive interference in one direction, you time delay the signal from the different parts of the array so that they are in the particular direction in phase, and in other directions they are not in phase. And in the same way here, the signal comes in from a certain direction, so it reaches the element with different delays, and then you adjust delays using a switch or something like this here, so that when you're leaving the surface, they have other delays, and that is sort of creating this type of beams in different directions. And we will come into in more detail how to do that. How can we configure things? Well, we can, for example, use this switch here to tune the impedance of the element, or tune the length of delay lines more mechanically, or you can have any kinds of phase shifter technology in order to change essentially how much time it takes from the signal reaches the surface until it is scattered. And a single element here doesn't make much difference. You can think about that as a solar panel. You don't put up this tiny solar panel on your rooftop if you would like to gather electricity from the sun. Well, you make a large one because you would like to gather a lot of energy. And sort of the same type of thing here. A small element can only capture energy proportional to its area. So you need many of them. How large are these elements then? Well, this is something we can choose as a designer. Of course, as a solar panel, the larger it is, the more energy it gathers. But we are not just going to gather energy, we're going to re-radiate it towards the receiver. And then it's important how large every element is, because this is sort of telling us what it will be the intrinsic directivity of the signals that are re-radiated. So ideally, we will sort of like have the ability, a signal comes in from a certain angle, and it can be reflected towards another angle, which we choose based on where the user is. And the color here is then showing some kind of change in the impedance over the surface, which is sort of deciding the delay it takes before that's retransmitted. And it's very hard to build a piece of surface material where you can change the impedance in a continuous way. So what people have in mind is to discretize the surface into small elements, and in each of them you have a constant impedance, but you can change it, as you can see here, of the colors. And let me show what could happen if a signal comes in from an angle of 30 degrees. So here is 30 degrees, and then I'm looking at what will be the gain of the signal in different directions, because always any antenna or element of any kind will have an intrinsic directivity. So a signal that is re-radiated will be directed in a particular way. And the red curve here is showing if you have each element here is half a wavelength times half a wavelength. If the signal comes in from minus 30 degrees, then Snell's law is sort of saying that if something comes in from minus 30 degrees, it's going to leave at plus 30 degrees. And this is what you can see here as well from the red curve, that in that direction, you have the strongest signals, but it's not like a perfect, like comes in from one direction, leaves entirely in another direction. It's sort of a beam with its main directivity towards 30 degrees. If you make the element lambda over 4 times lambda over 4, then you see that the variations start to be even smaller. So even if it comes in from minus 30 degrees and it has its strongest signals at plus 30 degrees, it's much more smeared out. And if you make it even smaller, like lambda over 8 times lambda over 8, you get the black curve here. And in that case, it's almost flat. And this is what we actually want. We would like every element to take a signal that comes in and re-radiate it almost uniformly in all directions. But didn't I say that you want the surface to beamform the signal in a particular direction? Yes, precisely. You want the combined effect of all the elements to lead to that. So if every element is sort of scattering the signals all directions, and then you can control the impedances so that you are phase delaying the signal or time delaying, and so that in certain directions they are aligned in phase, in other directions they are not, then you are able to focus the signals. So you want every element to throw out the signals in all directions, and then you delay them differently to create the directivity. So this is sort of the essence of how it works. And the vision of what it should be used for is to sort of create some kind of reconfigurable propagation world. So the RS as a whole should control the directivity of the signal, if the signals are absorbed or not, or you can even change electromagnetic properties like polarization. So here's an example of the library at Linköping University with the different floors here. And if you would like to cover all the floors, well, maybe you will have to put up base station in every floor. But what if we put up a base station at the top, and then we put up these surfaces at some different locations? And the signal that reach these surfaces are then beamformed into the floor where you want it to be. So if you're having a user at this floor, you can use this here to beamform to this user. If you have something at the bottom floor, maybe use this surface and so on. And that way you can improve indoor coverage as compared to a case where this is just concrete and the signal will just in a random way be reflected towards different locations. This way you can have more consistent performance. Suppose you have a meeting room here and you don't want anyone to eavesdrop on your wireless signals. Well, then maybe you can cover the entire room with these surfaces and make sure that the signals are either scattered inside the room, so they're never penetrating the walls, or they just absorb all the signal energy. And that's where you can protect yourself against eavesdropping. Or if you are in a city, here's me standing in a hotel room in Melbourne, then if you have tall buildings, it's very hard to put up a base station at a location where you can reach all sides of all buildings in the city. But if you put it up on some locations, and then you see that the base station can see the same building as I can see when I look out through the window here, but we cannot see each other. Well, what if we are putting up these surfaces at certain buildings here that we can both of us see, and then you can let those buildings reconfigure the scattering so that the signal bounces off that surface and reaches me, and I can then get a consistent wireless service at many more locations. This is sort of the general vision of this, and people have been calling this a number of different things over the years. Things like intelligent walls, or software-controlled meta-surfaces, or reconfigurable intelligent surface, which is what I have been using as the name in this talk, and which I think we are also sort of converging towards that name in the this scientific area. And there's also things like reconfigurable AI meta-surfaces, or intelligent reflecting surfaces. And yeah, if you look at this paper that I wrote in 2019, you can find a list of all these names and references to them. So that was my introduction, and now I will go over to the most technical part of the talk, where I will try to introduce some of the signals and systems theory and utilize it to explain how these systems work. So in signals and systems, we have a box, which is a system. You send a continuous time signal into it, and you get this continuous time signal out of it. And this could, for example, represent a communication signal, where X is the signal that we are transmitting and Y is the signal that we are receiving. And I have written PB here as a subscript, and that represents pass band. What does pass band mean? Well, it means that these signals are focused around a carrier frequency, which I call FC here. So in the frequency domain, maybe X have a Fourier transform, which is the red triangle here. And it has a bandwidth, B. So that is showing how large is the bandwidth area around FC where the signal lies. And this is how all of the wireless systems work. Someone buys a license to use 3 gigahertz, and then maybe you have like 40 megahertz around that carrier frequency. So then your signal needs to live there. And you send your signal through your system. The system is filtering it somehow, and what you receive is something that, if this is a linear filter, the signal, it lives in the same band as before, but it have a different shape in the frequency domain. It looks different in the time domain. How do we characterize something like this in signal systems? Well, if the system is what we call linear and time invariant, then that means that it doesn't matter when we are transmitting a signal. If it's time invariant, what we will see at the output is always the same. It's just shifted in time. And linear is something that also comes in wave propagation, that the propagation environments are linear. So you send a signal and it still lives in the same band afterwards when you receive it. But for linear and time invariant signals or systems, what happens is that you can characterize your system through what is called the impulse response. What happens if we send one strong signal that is very, very short, and what happens at the output? Well, if you define this function, which is the impulse response, then the received signal is to take the transmitted signal and the convolution with the impulse response. And this is the integral that you essentially are computing as a definition of convolution. But the star here stands for convolution. So as an example, say that you have a transmitted signal here, you receive a signal here. These are representing 2 antennas, and the signal is going directly. It bounces off this building, and it bounces off this car. Then there are 3 different paths here, and this 3 component here is representing them. So we have a direct path, the black one, where you get the transmitted signal that is delayed by time tau1, and it's also attenuated. That was what I talked about in the beginning, how it's sort of attenuated the further away you are. The green signal bounces off. It's received probably later because its path length is longer, and you will probably have lost more energy, both because of the longer path and because of losses in the reflections. And the same thing goes here for the car. The path from there have a loss and have a time delay. And when you have something like this, you see, okay, if I'm transmitting a particular signal, I get this weighted sum of delayed versions of it. If I would be transmitting what we call delta functions, these kind of impulses, then the impulse response will be what you get if you replace this with delta functions. This is the impulse response that you will have in a system like this. So this is just one way of describing a communication channel using signals and systems theory. Okay. In communication system, we are often developing all of our theory in what we call the complex baseband. And that is because we don't want to create theory that only applies for like 3 gigahertz spectrum. And then someone else say, oh, but we bought a 3.5 gigahertz license. And they say, oh, but then we need to start over from the beginning and develop new theory. That's not how it works. So what we are typically saying is that, okay, we're going to have a signal lying around some carrier frequency, FC. We don't care about what it is. What we care about is only the bandwidth, how large it is. And we call it a pass band because this channel is sort of passing through a signal that is in a particular band which is far away from 0. And it's of course a real valued signal, because signals in reality must be real valued. There's no complex waves in this particular way. But what we do in communication theory is that we always downshift these things in the frequency domain. So we take what we have in the frequency and we move it to the left here down to 0. And this is what I've done here. And the new function that I'm getting, I dropped the PB for passband, because now it is a so-called baseband signal. It's centered around 0. And if you have studied signals and systems, you know that the bandwidth is defined as the largest the segment on positive frequencies where you have non-zero signals in the frequency domain. So the passband here have B as its bandwidth, but here you should only start from 0 and count upwards. So you only get B over 2 as your bandwidth, which might sound very strange. How can you take a signal with have a bandwidth B and get the signal that have half of the bandwidth when you have downshifted it? Well, the thing is that this signal will be complex valued in general, because there are some properties for the Fourier transform that says that what you have at positive and negative frequencies must be symmetric if you should have a real signal. And if you just take whatever you have here in the real passband and move it down to the complex baseband, it's not symmetric anymore, as you can see for this triangle. It's not, you cannot flip it to get the same thing. So therefore, it's complex signals in general, and that's why all of the theory is complex in this area. And mathematically, the way to do the downshifting, or rather the upshifting, is that you create the passband by starting in the complex baseband, and you compute this type of operations here. So you shift it in frequency and you sum it up to get something that's symmetric. Okay, so what does this mean for us as communication engineers? Well, I was showing that if you transmitted the signal in a passband, you can have an impulse response, and you take a convolution between the transmitted signal and the impulse response, and then you get the output. You have the same type of relationship in the complex baseband. So if x of t is the signal, that you are transmitting in the complex baseband, and y of t is what you would have received in the complex baseband, then you can compute a convolution between x and something that they call the impulse response h of t, and it's related very strongly to the signal that I'm having in the passband. So you can take this passband impulse response that I was describing before, for example, a sum of different delayed copies of the signal, and then you have this e to the power of j2 pi fct with the minus sign here, and that is the only thing you need to add to downshift the channel. And you put it in here, you have all of the system theory. Okay, so let's apply this now to study a reconfigurable intelligent surface. So what are we actually doing here? We are transmitting a signal from this transmitter here, and we have a receiver that receives the signal. And the signal can reach from transmitter to the receiver directly, or it can reach this surface and say that the surface contains n different small elements, and each element is time delaying the signal, and then it re-radiates it. And hopefully we re-radiate it in a way where it's sort of focusing the signal towards the user. How can we describe this using sensor systems? Well, we can say that we transmit the signal X in the passband and receive a signal Y in the passband. And we can have this gray box here and say, oh, that end-to-end system is described by an impulse response HPV of T, just as I said before. And then you just forget what is at inside. You can apply all the theory I described, and we're done. But if you really want to study and optimize this surface, of course, we need to understand what goes on inside the box. So what goes on then? Well, the signal X will go over a direct channel with a certain impulse response going from transmitter to receiver. This is what all of the conventional communication theory is describing. Then you also have paths that goes via this surface. And there is actually n such path because you have n elements. And if you assume that these elements are not sort of coupled to each other, you're able to resolve all electronics effects. We can study them at n parallel lines here. So if you take the first element, the signal is propagating from the transmitter to the first element, and there is an impulse response describing that channel. Then the signal is entering the element. There is some kind of filtering happening inside the element, and then it re-radiates it. And that filtering is described by an impulse response. Then you have another channel from the first element to the receiver. That's just a wireless channel described by a filter or system with an impulse response. And then it goes on like this for all of the n elements. So you have n different channels to the RS, A, 1, 2, up to n. You have all of the elements here with the theta 1 to theta n described, and you have the channels from the RS to the receiver, B1 to Bn. So since wireless channels are linear, what is going to happen is that all of these n+1 different channels will sort of add up together here and form the received signal. And in that way, the impulse response will be the summation of the impulse responses from n different ways up for the signals to make it from the transmitter to the receiver. So you take the impulse response from direct path first, and you take a summation of the impulse responses from all of these paths here. And when you have like a chain of systems, one system, another system, and another system, you can take their impulse responses and take a convolution between them in order to see the joint effect of it. And that's also easy to see because so that the output of this one will be the convolution between X and A. And then it goes for another filter, then you get the convolution between what you had here and this impulse response, and then with this impulse response, and you get sort of a chain of this convolutions. That's what's described here. And what is then important to know? Well, people have been studying for many years how a wireless channel on its own behaves. It's something that's given by nature and which kind of reflectors you have around you. I just gave you one example of that. That means that the direct channel and all of the A channels and all of the B channels can be modeled in the conventional way. But what is particularly interesting is that all of these elements that you have inside the RS, this is something that we can control. So that's why I have written a theta 1 to theta n as an additional variable here. These are control variables. We can sort of change these filters over time, and we can do it in such a way that we can make sure that the end-to-end system here is as good as possible. And in that way, we are reconfigurable sort of the world around us in order to get better communication performance. So let me give you an example of that. And this is from a good paper by these authors here called Intelligent Reflecting Surface, Practical Phase Shift Model and Beamform Optimization. They are describing in one of the elements in the following way. You have a transmitter here. You say that the air that the signal is propagating over is like a transmission line with have the impedance given by the air. And then the signal is entering the element, and inside this element you have certain electrical it's viewed as a metal patch that have some resistance, and in particular it has a capacitance that we can control, and there are some other parameters as well sort of defining this circuit. And then from circuit theory, there is what is called a reflection coefficient that tells you what happens with the signal going from transmission, the incident signal here, to the reflected signal. Well, the reflection coefficient is giving you the amplitude and the phase shift that the signal is going to have. And in this paper, they sort of show how to compute this parameters here that is giving the impedance of the circuit. And here we have set 0, which is the impedance of the air. And I'm not going to bore you with all of the details, but here I'm going to show you the impulse response of this element here for particular values. So an impulse response is sort of in the time domain. If you are taking the Fourier transform on that one, it will tell you what the filter is going to do with different frequencies. And that will be something that is the description that is complex valued. So therefore, we often are dividing it into the amplitude response and the phase response. So to the left here, I'm showing the amplitude response for different frequencies. And I have set some values for L1, L2, and Rn here. and then I'm changing the capacitance of the circuit. And you can see that for 4 different capacitance, we get 4 different curves here. And my signal is at the 3 gigahertz frequency. So you can see that depending on which of the different capacitance we select, we get a little bit different amplitudes. In some cases, we get 0 dB, which means that essentially all of the signal that is coming in gets reflected. And sometimes we get minus, say, 1 or 1.5 dB, and that means that we are losing a little bit of the signals that is before transmitted, so sort of absorbed into heat. Why did I select this particular, you see, very specific numbers here? Well, that is because what happens with the phase response. So I've selected these numbers particularly to make sure that at 3 gigahertz, these 4 different curves are representing very different phase responses. So pi, 0, pi over 2, 0, minus pi over 2, and minus pi. This is sort of 4 numbers that are evenly spread out over the unit circle. And this will allow me to tune the re-radiated signal from an element up to pi over 2. And you can add additional values in between here and tune it even more. But that means you can essentially select the delay of the signal, and in that way you can tune for each element its delay, and you can form beams in different directions. And we will come back exactly to how to do that. But before we do that, let's also talk about how do we actually transmit data in a communication system. Because, yeah, so far I've been talking about continuous time signals, but we are not sending the data continuously. We have always a sequence, a discrete sequence of data. Let's call it X, M, and you have this kind of parentheses here, block that are describing that this is something going on in discrete time. So M is an integer. And what we do often when we are taking a discrete sequence of data and transmit it is that we are having what is called a pulse amplitude modulation to create the continuous time signal based on it. So we are taking each of the different elements in the sequence. We multiply them with P of t, which is a pulse form that we have selected, and then we delay it differently with the same index m divided with the bandwidth, and the bandwidth here is sort of saying how many symbols we are transmitting per second. So if you have 10 megahertz, we send 10 millions of these ones per second. We sum it up, and this is essentially how it looks like. So if my pulse shape is this red curve here, so it has a value between -1 and +1 if we are normalized time like this with the bandwidth. Then if the first symbol is 1, then we get 1 times the red one. If the second symbol is 2, we get a delayed copy of the same pulse, but with twice the amplitude. And if the third one is -1, we get the same as the red one, but it's delayed even more, and it's upside down. And then we add up the red, the blue, and the green, and we get the black curve. And this is what's actually being transmitted. And this is essentially how we are sending data in a wireless communication system. The pulse form, P of t, should be selected according to certain rules that you can find in system theory. There's something called the Nyquist criterion, which says that the pulse should be such that it's crossing 0 at particular times. Namely, every time we're sending one new symbol, all the other pulses should cross 0, so we don't see it at that particular time. And this is mathematically what the Nyquist criterion is saying. One of the classical ways of selecting something like that is the sinc function, which is sine divided by a linear, by its argument. And this is one way of selecting the pulse. And why do we have the Nyquist criterion? Well, the thing is that the transmitted sequence of data, x of m, is something that we are, this is data we would like to extract at the receiver. And how do we extract something from a continuous signal? Well, we sample it at the receiver. So the antenna is filtering something and then samples, and then we get our signal out of it. And the Nyquist criterion helps us when it comes to the sampling, because say that our received signal is just equal to the transmitted signal. So it's very simple. There's no filtering going on. There's no noise or nothing strange. Then if we sample the received signal at the time k, which is an integer, divided with the bandwidth, then we should take the signal that we were transmitting and put in the same k over b. And where does t appear? Well, inside the p. So we put it in here, and we see that we have k minus m divided by b. And if we have the Nyquist criterion satisfied, it means that whenever this integer k minus m divided by b is non-zero, we get a 0, so this part goes away. And then we get x over k, because it's only when m is equal to k that we get a 0. And at all other instances, m is not equal to k, we have an other integer here, and then Nyquist criterion says it's 0, so we just get the signal out. So this is sort of the way we pulse amplitude modulate the signal, so we get the continuous signal, we send it over the channel, we sample it, and everything goes right, we get only the signal here. But in reality, we have a channel, we have noise, so what happens if we put this together? Well, now the received signal, y of t, is the transmitted signal x, convolved with the impulse response of the channel, and then we have noise to it, which is Gaussian distributed typically. And what we do in the reception is now a sequence of things. First, it's like we know that our signal lies in a certain band because we have a passband signal from the beginning. It has a bandwidth that we know. But the noise that we pick up in our antenna is spanning over all frequencies. But we know that all the noise that is outside our communication band can be ignored. So the first step is always to filter with the sync function with having the right bandwidth, because in the frequency domain, that is just a box filtering out exactly the bandwidth where our signal lies. So that is the first thing to do. Filter the received signal y with such a box. And we can see that if y of t was this pulse amplitude modulated signal, we have a summation over our symbols. We have the pulse here, then we convolve it with the channel and with the pulse, this filter that we have to filter out the noise. And we get something like this, and we get the filter version of the noise. Next step, sample the signal, and it's set of t that we are sampling. We're sampling, as described before, as an integer divided by m, because this is how often we're sending new symbols. And then we get this x minus m divided by b here, k minus m divided by b, I mean, and then we have the noise here. And now, in signal to system theory, we often notice the following things. That if this received signal here that we have sampled, we call it set of k. This is now a discrete sequence, just as the data that we were sending. And p convolved with h, the channel, convolved with the pulse that we had from the beginning. This is sort of effectively how the pulse looked like. And this is going to become this Gaussian noise that have a certain distribution. And if we are just focusing our attention on a small enough amount of bandwidth, then any communication channel we have, as we saw before, you saw the impulse response we had of our filter was in the element was changing with frequency, but it did it over the gigahertz range. If we are focusing on just like 1 megahertz or so, then we will have that the filter is essentially constant. So it's just have one delay and one constant loss. And if we consider a small enough amount of bandwidth, then this pulse here will essentially satisfy Nyquist criterion. What we will get out of this is that this is having a constant value when we have something that is when m is equal to k, and otherwise from the Nyquist criterion this term is 0. So the sampled received signal is a constant times the transmitted signal plus noise. And now we are at the communication models that you usually see in textbooks on communication. But this constant can be characterized based on how our RAS-based system look like. So what will happen? Well, our direct channel had an impulse response. Typically, it involves some kind of loss in amplitude and a delay. And this is what happens in the passband. If we move it down to baseband, we add this e to the power minus j2 pi FCT that I mentioned earlier. And for each of the elements in the RS, each of them have an amplitude loss, alpha n on the way to the nth element, beta n on the way from the nth element to the receiver, and gamma n is describing the amplitude loss that we have inside of the nth element. And there are delays, tau and a. That is how the signal gets delayed to element n. And we have tau and b. That is how the signal is going to be delayed from the element n to the receiver. And tau, theta n, this is the delay happening in the nth element. And this is what we can control. So everything else here is set. And in the complex baseband, we take exactly the same thing. We add this e to the power j2 pi FCT term. And if we are putting these type of things into our model from before, we can compute that constant that I was describing that was in between the transmitted signal and the received signal. And that constant should contain this constant here for a direct path. And since there is a convolution involved, the t here will be replaced by the tau d that you have in your delta. And you get this term here. This is describing the direct path, its amplitude, and its phase shift. And then you have a summation over all of the elements. You get the multiplication of their different amplitude losses, because you have sort of a convolution between these three filters. And then you get this e to the power j2 pi FCT. And since you have a convolution involving delta functions, the t gets replaced by the delay. So you get the sum of their delays. So, in a nutshell, your transmitted signal is received multiplied with this factor containing different amplitude losses and different phase shifts. And this particular phase shift here, when it comes to the nth element, we can tune it. Whew. So that was all the system modeling. Let's now use the system model for something. So even if we didn't follow every detail in derivation, now we will just use this model so we can forget about exactly how we did it. So say that the signal that we transmitted gets multiplied with this factor that I described before. And now I omit the direct path for the moment. And what we would like to do is to tune this thing here so that the surface is in fact directing the signal towards a particular user, as I was illustrating earlier. How would we do that? Well, if you should try to improve something here in the terms of communication, the typical signal processing problem is to maximize the signal to noise ratio. And how do we compute the signal to noise ratio? Well, we take the signal power, we divide by noise power, and we multiply it with the amplitude squared. So this term here is sort of the complex amplitude. So if we take this term, we take this absolute value squared, we would like to pick the operation of this RS to maximize this channel gain, as I call it. This term that appears multiplicatively in the signal to noise ratio. And we can do that by selecting these phases here. So if we should select these phases to make this as large as possible, how would you do that? Well, we have a number of different terms that are going to be added up. And to make it simple, say that we have a term that is plus 4, and then we have a term that is minus 4. Well, they will cancel out each other. And that is because their phase shift is different. One is have a phase shift of minus pi over the other because it's negative, and the other one is positive. And if we add up numbers, it's quite easy to figure out yourself that you would like them to have the same signs. If everything is positive, they will add up as much as possible. And that can be generalized to saying that all of them could be pointing in the same direction in the complex domain as well. Then they will also add up constructively and keep their phase. And you can show mathematically, according to the Cauchy-Schwarz inequality, that if all of these terms here with expect e to the power j something is equally large, then its amplitude is 1, and we can drop this term and the maximum number is to sum up the terms, and then you just get the square root of the multiplication of these amplitude losses. And we achieve it when all of these different terms here are the same. so they're equal to some kind of constant that it doesn't depend on n, which tells us that how should we select our phase shift? Well, we should select the phase shift so that we are adding something to tau NA plus tau NB so that we always get the same constant. And since we cannot add a time delay that is negative, because then the signal would have left the surface before it's received, we must find a minimum positive solution to this, which is what I am giving here. You find the largest delay that you get over the communication channels, over all of the M elements. And then for that particular element, you select tau theta n to be equal to 0. So that for that element, you are re-rating the signal immediately. And from all of the other signals, you are adding additional delays, as you can see here, by so that we get something that's positive. And in that way, we are making sure that all other different paths coming from the surface here are being received at the receiver at the same time. And if all of the paths have the same alpha, beta, and gamma here, we can drop the n, and then you sum up terms that are the same. You have n of them, and you square it, you get n square, and you get rid of the square root here. So we can also say that the SNR is sort of scaling with n square, alpha, beta, gamma. And what this is effectively meaning is that we can, conventionally, if we have a metal surface, the signal comes in, it bounces off the surface, and the sort of Snell's law is saying that the angle of incident is the same as the angle of reflection, but on the other side of the normal here. What we are doing is that we have the same surface here, but within the surface, in different pieces of it, we are tuning the delays in such a way that the signal behaves as if it had, or the surface behaves as if it was at a different location. That is what's over here. So the signal in this parts here are being delayed and more than the ones over here. And in that way, you're essentially using the surface that looks like this, but it approximates being like this. And then the reflected signal will be towards a user at a particular location. And actually, it's not even exactly like this that's going to happen if you are focusing the signal at the user. In this case, the user will be infinitely far away. Then this is what's going to happen. If the user is close by, it will. What you will actually do is to focus the signal. All pieces of reflected energy from the surface will be focused entirely at the location of the user. So it's sort of like having a bended surface where you delay things, the green thing here showing how it's delayed, and that way you are focusing both the directivity of the reflected signal and you are changing the shape of the signal, so you really are focusing as a lens towards the location of the receiver. And I'm slowly running out of time, but I will just briefly say that if you add a direct path to things, this solution becomes essentially the same. You would like all of these paths here, both the ones you can control and the direct path that you can't control, you would like to make sure that they all have the same phase. So you select your phase shift to achieve that. And when that happens, you can just sum up the amplitudes like this and square it. And this happens when you make sure that the delays here of the RS elements is sort of matching this ones. And it might not be a perfect that they become exactly the same, because typically the direct path is faster than the reflected ones. So we should actually add things here also like this, where you can add a integer divided by the carrier frequency, which is sort of adding, you can add 1 period or 2 periods or so on of the carrier in order to find a solution to this. But I don't want to go into all of the mathematical details here, but end with 2 simulation examples to show what the benefits of this technology is going to be. So say you have a transmitter transmitting to the receiver, and then you have the RS here, and the path loss from the transmitter to the RS is minus 75 dB, and then you have minus 75 dB here as well. And then you have 2 cases when the path loss between the transmitter and the receiver is either minus 100 or minus 75 dB. We have some transmit power assumptions, I think like that. Then what is the spectral efficiency in bits per second and hertz that you get, then depending on how many elements you put here, you will be able to reflect the signal in different ways. If we don't have any elements at all, you get these two dashed lines. The upper curve is in case number 2, when you have a good channel. This is what you have. The direct channel is rather good, then you get the upper one. If it's bad, you get the lower one. And if you now have an RS, and you increase the element from 1 up to 1000, you see the red curves are improving. And the improvement is particularly large when the direct path is weak from the beginning. Then you see a much bigger improvement, much faster than if you have a rather good channel from the beginning. So this is sort of showing that an RS is particularly helpful when the direct path is relatively weak. So these are cases where you should use this technology. So with that in mind, what are good use cases then? Well, whenever you have a bad channel, you can always deploy more base stations. This is sort of the conventional approach, but that is very power hungry. When you get very many base stations, as we already have, it will be power hungry. You will need a lot of infrastructure to control a system, and you will get a lot of interference between the cells. So this is sort of the resource that we are running out of now. If we would instead think about other solutions, there are things like relays that are being used today to put up to increase the range of things, and one could do something like that as well. Or you can try to change the building materials, remove all the walls in the world, and then you'll have better wireless propagation, but you won't really have that. You can't really do that in reality. So maybe the relays is the closest thing you can compare to. So let's do that. Let's say that you have a transmitter sending a signal to a receiver, you have an object that's blocking most of the signal, and on this wall you either put up an RS or a relay. In particular here I'm showing something called a decode and forward relay. Then what I'm showing here is the signal to noise ratio that you get on the vertical axis, depending on how large the IRS is, or the decode and forward relay. So sort of saying how large is the antenna array. So you have two curves. The dashed one is for a decode and forward relay, and the blue one is for an RAS. And what you can see is that if you would like to have the same SNR, you need to have a much larger RAS as compared to a decode and forward. Why is that? Well, the RAS is sort of just taking a signal that reaches it and reflects it. While the decode and forward relay, that is a piece of equipment with an amplifier that is amplifying the signal and retransmits it. So the good thing is that it can be small, but the bad thing is that it needs to have an amplifier. So you can say that sort of one of the benefits of an RS is that you trade away the need for having an amplifier in your surface by instead needing something to be larger. So that is sort of the trade-off between a large RS or a small decode and forward relay that requires a power amplifier and much more power to operate. But still, I don't think that beating a relay in terms of that is really a good case, because maybe you will need to have something that's a meter by a meter tall in order to beat a relay. I think there are other properties that is much more useful in order to improve performance in this type of systems. So here's an example of that. Say you have a transmitter with two antennas, you have a receiver with two antennas. And if you transmit the signal in line of sight to this receiver, even if you have two antennas, it will see very similar copies of the signals. The channel will, so to say, have rank 1, which means that you cannot use the channel in order to send one signal to one antenna and another signal to the other antenna. It won't work out. But if you have an RS at this wall here, you can tune it in such a way that you are improving the channel. So here's an example of that. The rate that you get in bits per second and hertz. The black one here is if you only have a direct path, you get a certain rate. If you are tuning the RS in order to maximize the signal to noise ratio, so getting a strong signal as possible here, you get the blue curve, and you need a certain number of antenna elements in the surface in order for it to work out. If you are not trying to maximize the signal to noise ratio, but instead trying to make sure that you get a rank 2 channel, so the two different antennas here are now receiving sufficiently different signals so that we can send two streams of data from transmitter to the receiver, then you get the red curve. And now you have a big difference. So I would say that if you operate it just to maximize SNR, well, the gain is not that large, and conventional relays could probably be as good as it. But if you start to do other things like improve the rank of the propagation environment, you can do much cooler things and really utilize your ability to change the propagation conditions. So I think we should think more deeply into how we can use these surfaces in order to improve the propagation conditions beyond just improving the signal to noise ratio, because there's much more to do. Here is a slide that I might skip over. You need to somehow reconfigure the surface and figure out how to do it, because the RS itself might be blind. So there are procedures that people have been proposing on how you would just try out some different ways of configuring it and figure out which is the best one. And there is a nice video from the University of Surrey where they are demonstrating how to do that. So I recommend you to view that one if you're interested in how it works. And to wrap up, is a reconfigurable wireless world possible? Well, it's easy to say that the transmitter and receiver cannot be controlled in conventional technology. Now we can control them with this one. We can control the entire propagation environment, something like that. But in reality, we put up a surface that might be 0.5 meter times 0.5 meter, and it can control a small piece of the propagation environment. But that might be enough, because if you only are achieving or receiving 1 billion part of the transmitted energy, a small piece of equipment can double that or triple that, and that could be enough to make a big difference. And you can always put up a big MIMO array instead. I'm a massive MIMO researcher. You can put up an active base station at the same location, but that would be very costly. You cannot put it everywhere. So sort of the RS characteristic is as a cost and energy efficient alternative to other technologies, which I think is particularly well suited to improve conditions like the rank that I was describing. And there are also things like macro diversity, that if you are in a room with a lot of objects, if you have a bigger surface, there's a bigger chance that you see some pieces of it than if you just put up one transmitter that's small. And I personally believe that this have most of the use cases when we move up in frequency. Because if you are operating above 100 gigahertz in the future, the signal will be easily blocked by your hand or by other objects. But if you make the surfaces large, you will hopefully have the ability to send the signal via some parts of the surface. And I also think in terms of people working in academia right now, this is a great research topic, because there's a lot of uncertainty about even the fundamental aspects. So there's a lot of things to explore as compared to a lot of the things that are already in the 5G that have been explored for decades. So with that, if you would like to know more, I have, as was mentioned before, a YouTube channel where I have been describing some of these things in previous talks, and most of them are containing different slides than this talk. And I also have a podcast I've been talking about this called Wireless Future. And finally, here are some key references, and I can highlight there is an upcoming paper called A Signal Processing Perspective on Reconfigurable Intelligent Surfaces with Wireless Applications, which will appear on Archive in February, because we are not entirely done with it yet. But some pieces of this talk was a sneak peek of what we will describe in that paper. So I recommend that one. So that's me.
So thank you, Emil, for this very nice talk, very interesting talk, and very nice slides. So now we can take up questions. So I already saw about 10 questions that I put in the Q&A box. But I invite audience now to also ask their questions in the Q&A chat box, and we will see how much we can answer. So perhaps we're going to pick a few of them in the interest of time and answer them. Okay. So let's start with the easy ones, I guess, first. Okay, so yeah, so Amin is asking what are the differences between holographic beamforming, IRS, and conventional beamforming?
Yeah, this is a good question, because I can first say that some people might have different views of this. So I'm not saying that what my answer now will be the what everyone will agree upon. But I think that these three things that were mentioned are different things. So conventional beamforming is that you have an array of antennas, you generate the signals, you send it into antennas, and then because you have an array of antennas, you will get signals directed in a particular direction. A holographic MIMO, this is sort of taking the same concept as I was describing now, but instead of having a transmitter at one location, a surface at one location, and a receiver at the third location, the surface is at the same location as either transmitter or the receiver. So you sort of put the transmitter, for example, at the back side of the surface. You connect it to each of the elements directly with cables, and then you can still tune the impedances of the elements in order to do beamforming. And then RS here, what I was describing, was something where these three pieces, transmitter, receiver, and surface, is at different locations. And that is what is, I think, the most interesting research area, because it hasn't been explored very much. There are already holographic MIMO type of products with metamaterials being used in by Pivotal Comware, Chimera, and some Chimeta, I think they're called, and some other companies that are selling products that are using this for arrays.
Okay. Mohammed is asking a couple of questions. I did not see the slide number. Perhaps he has noted it down. He's saying that in slide 8, how do the graphs change if the incident angle is changed from minus 30 degrees? Does only the peak shift, or the average and the shape? I think he's referring to the this one, perhaps. Yeah.
Yes, so I think as long as this the incident angle is somewhere where in the middle, say minus 45 to 45, I think it will mainly be that it is shifting here. But then if you sort of get the signal coming in very much from the side of an element, you will not get exactly the ability to radiate it equally in all directions here. So there will always be some kind of directivity. You cannot sort of expect I mean, if you look yourself in the mirror, if you're standing very close to one of the edges of it, you will not be able to use it very much, because you will see the distorted version of it in the same type of thing. But yeah, it will be a fairly large angle where I think it's going to work out fine.
Mm-hmm. So there's also one more question related to channel estimation, I guess. In a multi-path environment, how is the incident angle to the IRS determined? Do we always need to assume an LOS path between the transmitter and the IRS?
No, you don't need to do that at all. So in this talk, I was assuming that you know the channel, and there are some various approaches to try to estimate them by trying out different angles and things like that. But more generally, if you can estimate things, no, you don't need to have a particular structure of the channel. But the more structure there is that you can guarantee, the better you can make your estimation algorithms. And it's like always when you try to estimate something, the more prior information you have, and the more that prior information is structured, saying that you have a line of sight channel, the easier it will be to estimate. And I would say in general also, what I would describe now as a narrowband channel, if you have a more wideband channel, where you have frequency selective fading, the problem is that the RS will need to be concentrated on just a few of the paths. So if you have many paths and they're equally strong, this technology won't be as powerful anymore. So I think in general that we should think about cases when you have line of sight paths to and from the RS, but not between transmitter and receiver. That is when its technology will be as useful as possible.
Mm-hmm. Okay. And related to channel estimation again, so what is the channel estimation overhead with and without IRS?
So without an RS, it's all of the classical type of thing where you, if you have a narrowband channel, you sort of need to send one signal per transmit antenna. And that's it to get the degree of freedoms that you want to have. If you have an IRS involved here, the complicated thing is that if you have n elements here, you will it will look like you get n dimensions. So you will need to spend a large number of signals on learning type of things because of that. So if you have 1,000 elements, it's like 1,000 dimensions. But there's a lot of structure that one needs to be aware of. One thing is that if you squeeze many elements together, you're not increasing the dimension of things. It's the total size of it that matters, and not how large the individual elements are. So their channels will be correlated. So that can be utilized to make it simpler. And if you are in line of sight scenarios, the important thing is to use that parameterization in order to learn the channels better. This is an ongoing topic, and I cannot give it a specific number. But I think this video is showing nicely that if you are in relatively simple propagation environment where you focus on line of sight, you can do it. It's not that complicated.
Okay. So I guess a couple of more questions before we can wrap up. Okay, so this is a bit long. So it seems that the fabrication of oversampled with sensor spacing less than half wavelength antenna arrays looks difficult at millimeter wave frequencies, say 60 or 100 gigahertz. How difficult is this fabrication of RIS panels for millimeter wave scenarios compared to fabricating antenna arrays? And second question from the same person, he wants your thoughts on the role played by RIS in beyond 5G communications.
So when it comes to the first question there with hardware, I recommend one of the reference that I have in paper 3 here on the 3 myths and 2 critical questions, which is pointing towards the state of the art on the experimental works there. And there are implementation. So if you just think about how to create the surface itself and don't care about the signal processing that is needed in order to configure it, then people have been working for decades on these type of things. And the research is spanning all the way from like 1 gigahertz up to the optical ranges. So printing this type of meta surfaces using a variety of different materials, from what we are used to from building antennas for RF up to using graphene and other materials at higher frequencies. There are a lot of concepts around that. And so it is possible to build these things in various sizes already. I don't say that it's a solved problem, but there is a lot of research around this type of things that I recommend to read. What was the second question? What's this going to be used for?
Yeah, role of RIS in beyond 5G.
Yes. So some people might be saying that this is the 6G defining topic. And first of all, I think it's way too early to say anything about what 6G actually will be utilizing. Second of all, I don't think this is going to be the main thing of technology in general. You can think about, we had relaying technology for 100 years, and it's been supported by maybe 2G even, but 3G and 4G and now 5G relays are supported. You can talk with your operator, and if they agree upon, you might be allowed to put up a relay somewhere to improve your coverage. And given that they are not utilized so much so far, one could question how often we will actually have scenarios where these things will work out very well. I think it will be specific scenarios at higher frequencies when you have a particular room that you would like to cover, or a particular factory or something like that where it can be useful. So maybe when you're thinking about now like private 5G networks for specific company premises, for example, in those type of scenarios, using this type of technology in the future to improve the coverage, so might be a useful type of technology. I don't think it will be a mainstream technology to be utilized anytime soon.
Okay, so we'll take this last question. It's because it's asking for a clarification and also your thoughts. In slide 21, in order to focus the signal towards a particular user, we need to know the delay values in a particular instance, both in user IRS, transmitter IRS paths. So how do we actually obtain these delays in a changing environment? Again, related to how do we know the channel, which you assume to be known. So how much resources do we need to obtain? What he's trying to ask, I guess, is want to focus the signal accurately to a particular user, what is the precision of the delays that we need to have? I'm just rephrasing the question that he's asking.
Yes. So I would guess that in many applications, the precision will be mainly limited by the hardware that you are having in the surface. Because even if I did sort of a mathematical expression where you can select a real valued number for the delay, for example, I think in reality you will have, as in the examples I was showing, like 4 different states with 4 different phase shifts, and then you pick the best one out of those ones. And it sort of results in that we should roughly be informed in the right direction. It doesn't have to be exactly at where the user is or something like that, but if we can just make sure that all of the signals are positive and have a positive real part in the right direction, well, then they will approximately add up, and then they will at least never cancel out each other. So that would be enough. Then in terms of really quantifying things, well, if you make a stupid implementation, it's a simple, naive thing. You have n elements, then you turn off n minus 1 of them, you send a signal, then you can estimate the delay. And then you do this sequentially for all of the n elements, and then you have a estimate of how they are delayed differently, and then you can use that to figure out how you should tune the delay so they all become roughly the same. So that could be done as a simpler solution. And if you then also utilize that there is structure in the world, the elements will be packed closer together, so the delays cannot vary very quickly. Well, then you can utilize that to cut down it substantially.
Okay. So I guess, with that, I would like to conclude this webinar, and thank you once again for accepting our invitation and giving us this very informative, very nice talk on RIS. Thank you, Emil.
Thank you very much for the invitation, and thank you for tuning in and watching it online.
Thank you.